Hello everyone, my name is Lakshnanwani and I am a master's student at IIIT Hyderabad working with Robotics Research Center, and today I will be presenting our work on instance level semantic maps for vision language navigation. At our lab, we extensively experiment with mobile robots, and the recent advancements in vision language navigation (VLN) have motivated us to enhance our robots' capabilities for handling such complex tasks. To achieve this, we conducted a comprehensive literature review and came across the paper VL Maps, which presented an effective approach for VLN. However, we identified a crucial limitation in prior works, as they primarily focused on understanding the environment semantics, overlooking the differentiation of various instances of the same object. This limitation hindered their ability to handle queries that require the robot to navigate among relative locations of objects, such as navigating to the fourth table in the field of view or going to the second chair on your left. To address the challenge of capturing instance information and enriching semantic understanding, we devised a novel mapping pipeline, resulting in the creation of semantic instance maps, or SI maps. By incorporating language understanding through ChatGPT, we enabled our robots to perform navigation tasks based on instance-based queries. During the development of our mapping process to capture instance information along with semantic understanding, we encountered three key sub-challenges that we needed to address in order to achieve success. First challenge was to correctly associate instance IDs of the same object across different frames. Panoptic segmentation models identify object instances in the current frame without considering the context of other frames, leading to inconsistent instance IDs across frames. Resolving this issue was crucial to ensure accurate tracking of instances across the entire sequence of frames. The second challenge arose due to the imperfections in panoptic segmentation models. In certain scenarios, the models may misclassify objects or entirely misdetecting some objects. Dealing with these inaccuracies was vital to maintain the integrity of the generated semantic instance maps. The third challenge we faced was the presence of multiple instances of an object in close proximity to each other in real-life settings. This proximity rendered traditional clustering methods such as connected components on grid cells ineffective in distinguishing individual instances. Overcoming this challenge was essential to ensure accurate and separate identification of closely located object instances. After thorough consideration of these challenges, we devised a pipeline to generate semantic instance maps that successfully addressed the subproblems and provided a comprehensive solution for vision language navigation. Our mapping pipeline involves the following steps. Utilizing mass deformer on each RGB frame to obtain panoptic segmentation. Back projecting the semantic and instance information onto a top-down 2D grid map using depth images and pose information from the current frame. Creating nodes for each object when a new semantic label is encountered in a grid cell, and updating edge weights using instance information. Registering all frames and applying community detection on the generated graphs to identify different instances. Finally, performing a post-processing step to obtain the final global instances. As depicted in the presented SI maps, each grid cell stores both semantic and instance information, allowing us to carry out navigation tasks based on instance level queries. Recognizing ChatGPT's growing popularity in the robotics community, we leveraged its complex language understanding and code generation capabilities to integrate it with our maps. For this purpose, we developed 23 function primitives, each assigned with a specific task using SI maps and the required object with its relative instance for navigation. By providing ChatGPT with detailed explanations of these functions, we prompted it to generate working code that seamlessly combines these functions to achieve the desired task. With some interactions to reinforce ChatGPT's understanding of the functions and our requirements, it could produce code that the robot can directly execute without manual intervention. The navigation pipeline illustrated in the flowchart encompasses the following steps. Receiving a language command and extracting the required object and its relative instance for navigation and generating a working code using them. Applying regional mask to the SI maps based on the user's input and defining where the robot should look for the object, example in its field of view. Selecting the goal instance using Euclidean distance from the current location. Generating a trajectory using the A-star algorithm to guide the robot towards its destination. In the accompanying demo, you can observe the navigation pipeline in action. The demo features a more complex command highlighting the importance of accurate interpretation of input queries and precise semantic and instance information. A slight misinterpretation could lead the robot to an undesired location, resulting in task failure. For this demo, the user asked the robot to navigate to the nearest sink, then to the stairs, and subsequently face the chair behind the stairs and navigate to the fourth chair visible to it. Please note that the robot follows the A-star trajectory without additional trajectory smoothing or local planning, which may result in a slightly jerky motion. To validate the semantic instance maps generated by our pipeline, we evaluated the navigation performance in simulation using ground truth maps, VL maps with and without connected components, and our SI maps. We employed both automatic and human evaluations to measure the success rate. The results clearly demonstrate a significant improvement in performance using SI maps compared to the baseline, with a remarkable 46% increase in human evaluation scores. In conclusion, our research emphasizes the importance of presenting instance-level information to robots for autonomous navigation tasks. By creating semantic instance maps and integrating ChatGPT, we enable our robots to better understand and execute complex language-based navigation queries. Thank you all for your time, and I am open to answering any questions. Thank you.